Hello, and welcome back to Shiksa DaCosta. Today we're going to learn about some right bisectors. In this lesson, you'll learn how to ascertain the coordinates of a point that's right in the middle of a line segment if you're given its endpoints. And you'll also learn how to find a perpendicular line segment. To start off, look at all of these polygons. All of these are quadrilaterals. They all have four sides. And ask yourself, which of these have diagonals that look like they bisect each other? Now remember, bisect means to cut in half. Which of them have diagonals, which means a line that goes from one point to the other? And let me show you an example of that here before you start. So this square, if I draw a line from one corner to the other and one corner to the other over here, do these lines cut each other exactly in half? In other words, do they bisect each other? And once you do that for all of them, once you check that out, which of the bisectors look like they meet at a 90-degree angle? Which ones are perpendicular? Pause the video here for as long as you need to answer these two questions. So just looking at the square here, all of these side lengths are actually the exact same length. So because this side length is the same as this point must be exactly halfway through, and same for this diagonal over here. If I look at the rectangle, it creates a very similar shape with its diagonals. These two are the same length, and these two are the same length. In the parallelogram, these two are the same length, but actually because these points are at an angle here over that this angle is a little bit wider than this one, it's almost like this line I think is a little bit shorter than this one. And because of that, they definitely can't both be the same length, but this does look like it goes through the middle. It looks like this length is the same length as this one over here. So they do bisect each other, even though they are not the same lengths, all four of them. The rhombus, yep, that goes right through the center. This and this look like the same length, but these two, the rhombus looks like it's a little narrower than it is tall, and so these might be the same length, and these might be the same length as each other, but they're not all the same length. In the trapezoid, when I draw those diagonals, it actually looks like maybe these two are the same, and these two are the same. And finally, for the kite, here we have these two look like they're the same length, and these two look like two separate different lengths altogether. So I'll put 2 notches here and 3 notches here because none of them look like either of the other lines. So which ones bisect each other? A bisector, remember, is a line that's cut exactly that cuts another line in half. And so certainly both of these got cut in exactly in half. Same with the rectangle. The parallelogram did get cut in half. Both of the diagonals got cut in half. Even though this diagonal was bigger than this one, this portion is half of this diagonal. This portion is half of that, the other half of that diagonal. This portion is half of this diagonal, and this portion is the other half of this diagonal. So they do bisect each other. The same thing applies to the rhombus, but the trapezoid and the kite, if you look at a diagonal, one side has a different length than the other side, and so it has not been cut perfectly in half. These two are not bisectors. These diagonals don't bisect each other. Whereas for perpendicularity, we're looking for a right angle. Do these look like they meet at a 90-degree angle? Yep, that is perpendicular. But these look like this angle is a little bit wider than this one, and so I would say this is not perpendicular. Same with the parallelogram. The rhombus we can very clearly see over here meets at a right angle. The trapezoid doesn't, and the kite does. So the only shapes that have diagonals that bisect each other and those bisectors are perpendicular are the square and the rhombus. Now I want you to take a look at this diagram, pause the video here for as long as you need, and ask yourself, what do you notice? There are lots of things to notice about this. One of the things is this pink line here and this pink line here both have 1 notch. And this green line and this green line here have 2 notches each. That would indicate that those are the same length. And because they form a right triangle, these form a right triangle as well, which means that this length must be the same as this one. We would call this length over here, the amount to go from O to B, the horizontal distance you must travel, we might call that the run, whereas we would call this the rise. And now notice that the run over here, the vertical distance is always the rise, the horizontal is the run. So this run is actually the same length as the rise from this triangle. And the rise over here is the same length as the run. The last thing you might notice is that this green line and this green line would meet if I extended it all the way down. It would meet at a 90-degree angle. And we can even see that happen with the pink lines here. And what that must mean is I kind of took this triangle and I rotated it this way. And that's how I ended up with this right triangle. And if this is 90 degrees, that means that it was a perfect 90-degree rotation, making this angle over here 90 degrees as well. And so these two lines are perpendicular. And one thing we can take out of this, this diagram is that in order for two lines to be perpendicular, their slopes, which is rise over run, are very closely related. The rise, which is normally in the numerator, of the one line segment must be the run of the other line segment, and the rise for the first one must be the run of the second one. So these basically switch places. The other thing to note is if I just switch places, I would end up with a line that sort of goes out like this. But mine is actually going downwards. And so not only does it have to be, do they have to be the reciprocals of each other, but they also have to be the negative sign of each other. We'll use that idea about negative reciprocals being a perpendicular slope to see if we can find something called the right bisector. A right bisector is a line that bisects something. So we're looking for the right bisector of this line segment. So this line should cut this line segment exactly in half. It also is a right bisector, which means that it needs to meet the line perpendicularly at a 90-degree angle. So let's see here. I do know that in order for this line to be cut in half, the bisector has to go through the middle, which is about here. I'm going to label that point C. And that's right in the middle of A and B. And so if I take these 2 points here and I draw a triangle, sort of like that, you might notice that, well, you know what? Why don't I give you a chance to figure this out? Pause the video here and see if you can find out anything about the line that would meet this line at a 90-degree angle and also bisect it by going through it right in the center. So I did get you off to a pretty good start, but let's see where we can go from here. So if I draw this right triangle here between A and C, and then I move it over just like this, you might see that, hey, those are actually the exact same distance, because C, and that makes sense because C is in the middle. So this distance must be the same as this one. Now, if we look at the bigger right triangle that we've got here, this is the rise, or sorry, the run, and now right now it's 12, right? 8 on this side, 4 on this side. This is the rise. And the run seems to be, or the run of the yellow triangle seems to be half the run of the larger triangle. And similarly, the rise over here is 16, whereas this rise and this rise must both be 8. And that's how I might get to the middle point right here, geometrically. And the learning that I might take away is, for this point, the x-coordinate always has to be exactly between the x-coordinates of the two endpoints. So if I add up 8 and -4 and divide that by 2, I'll be finding the average between those two numbers. And that gives me this number right here, which is 2. I can do something similar for y. That's where the coordinate has to go on the y-axis. And we can see that that distance and that distance are identical. And that means that this must be right in the middle of the endpoints y values. And to find that out, all I have to do is take ya and yb and just average them together. Add them together and divide it by 2. The last thing to note before we move on is the slope of the line segment AB is up by 16, that's the rise, the run is 12. So why did I do all that to find the slope? Well, one thing to know is my line, the right bisector, has to go through the line at this point, but it also has to do that at a right angle. And I need the slope to figure that out. So the slope between A and B is clearly 16 over 12, but we can reduce that fraction. And actually, we will end up getting the same ratio between any 2 points on that line, including A and C. The slope between between AC, that line segment, is 4 over 3. That's the same as the slope up here. That's the same as the slope of the larger triangle. And what this implies is that a perpendicular line would have a slope of 3 over 4. That's the reciprocal, and negative. And that line would kind of look like that. Right? So if the rise was 8 and the run was 6 here, we're going to flip those two around. And that would imply that the rise is negative 6 over here, and the run is positive 8. And so for line segment AB to be bisected, it has to have a slope of negative 3 over 4 to be perpendicular. To be bisected, that line has to go through this point, C. And so we can find out the equation of this line. Remember, the equation of any linear relation has only two parts, the slope, which we already know, and the y-intercept. And to find the y-intercept, we just need a coordinate on this line. Fortunately, we have one. And I'm going to be able to plug in the y value of c, which is 2, equals the slope of my line, which is negative 3 over 4, times the x value of c, which is 2, plus b. 3 over 4 times 2 is 1.5, and of course times the negative is negative. And then if we add 1.5 to both sides, we'll find out that the value of b is about 3.5. And actually that makes sense. When I drew my sketch, I can see that right there it goes through the y-axis. So the equation of the perpendicular bisector in this case is negative 3 over 4x plus 3.5. In a nutshell, the midpoint of a line segment is pretty easy to find. You just average the x-coordinates of the endpoints and the y-coordinates of the endpoints as well. A line is perpendicular to another line if their slopes are the negative reciprocals of each other. If you're looking for the equation of that right bisector, you just find the slope of your original line, rise over run. You make it its negative reciprocal to find the perpendicular slope, and then substitute in the point M for x and y to find out exactly when it's going to reach the midpoint. Find the midpoint of the line segment AB if these are the coordinates of A and the coordinates of B rounding to the nearest tenth. And here is the formula in case you need that. Well, the midpoint of a line segment, and sorry if you didn't get the chance to, please go ahead and pause the video and see if you can do that by yourself. All right, well, hopefully you're able to recognize that the x value of point A is 55, the x value of point B is 2 pi, the y value of point A is negative 2, and the y value of point B is 3 over 7. And the coordinates of the midpoint, when we plug them in, we can find them out just with this expression to find the x and this expression to find the y, and we're going to round that to the nearest tenth. So I'm just going to put that entire expression in on my calculator, and then hit equals, and that will resolve it for me, and I can just round these values to 1 decimal place, and to find out that the midpoint of the line segment AB is at about 30.6 and negative 0.8. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.